A dive bomber is a bomber aircraft that dives directly at its targets in order to provide greater accuracy for the bomb it drops. Diving towards the target simplifies the bomb's trajectory and allows the pilot to keep visual contact throughout the bomb run. This allows attacks on point targets and ships, which were difficult to attack with conventional level bombers, even en masse. Definition: a dive bomber dives at a steep angle, normally between 45 and 90 degrees, and thus requires an abrupt pull-up after dropping its bombs. This puts great strains on both pilot and aircraft. It demands an aircraft of strong construction, with some means to slow its dive. This limited the class to light bomber designs with ordnance loads in the range of 1,000 pounds, although there were larger examples. The most famous examples of the Junkers Ju-87 Stuka, which was widely used during the opening stages of World War II. The Aichi D-38 Val dive bomber, which sank more Allied warships during the war than any other Axis aircraft, and the Douglas SBD Dauntless, which sank more Japanese shipping than any other Allied aircraft type. The SBD Dauntless helped win the Battle of Midway, was instrumental in the victory at the Battle of the Coral Sea, and fought in every U.S. battle involving carrier aircraft. A second and simpler technique is to bomb from a shallow dive angle, sometimes referred to as glide bombing. This reduces the accuracy, but still allows line of sight to the target during the bomb run. The Junkers Ju-88 and Petlikov P-2 were widely used in this role. The Heinkel He-177 is often mentioned as having its development upset by the demand that it be able to dive bomb. Although this actually referred to glide bombing, the phrase glide bombing should not be confused with the term glide bomb, where the bomb glides towards its target while the aircraft remains in level flight. Attachments for this type of bombing were fitted to the Norden bombsight, but in practice this proved unworkable. Dive bombing was most widely used before and during World War II. Its use declined during the war, when its vulnerability to enemy fighters became apparent. In the post-war era, this role was replaced with a combination of improved and automated bomb sights, larger weapons and even nuclear warheads that greatly reduced the need for accuracy, and finally by precision-guided weapons as they became available in the 1960s. Most tactical aircraft today allow bombing in shallow dives to keep the target visible, but true dive bombers have not been a part of military forces since the start of the jet age. Bombing accuracy. Horizontal bombing. When released from an aircraft, a bomb carries with it the aircraft's velocity. In the case of a bomber flying horizontally, the bomb will initially only be traveling forward. This forward motion is opposed by the drag of the air, so the forward motion decreases over time. Additionally, gravity accelerates the bomb downward. The combination of these two forces, drag and gravity, results in a complex pseudo-parabolic trajectory. The distance that the bomb moves forward while it falls is known as its range. If the range for a given set of conditions is calculated, simple trigonometry can be used to find the angle between the aircraft and the target. By setting the bomb sight to this range angle, the aircraft can time the drop of its bombs at the instant when the target is lined up in the sight. This was only effective for area bombing, however, since the path of the bomb is only roughly estimated. Large formations could drop bombs on an area hoping to hit a specific target, but there was no guarantee of success, and huge areas around the target would also be hit. The advantage to this approach, however, was that it is easy to build such an aircraft and fly it at high altitude, keeping it out of range of ground-based defenses. The horizontal bomber was thus ill-suited for tactical bombing, particularly in close support. Attempts at using high-altitude bombing in near proximity to troops often ended in tragedy, with bombs both hitting the targets and friendly troops indiscriminately. In attacking shipping, the problems of inaccuracy were amplified by the fact that the target could be moving, and could change its direction between the time that the bombs were released and the time that they arrived. Successful strikes on marine vessels by horizontal bombers were extremely rare. An example of this problem can be seen in the attempts to attack the Japanese carriers using B-17s at altitude early in the Battle of Midway. With no hits scored, the German battleship Tirpitz was subjected to counter-attacks, many while in dock and immobile, but was not sunk until the British brought in enormous 12,000-pound tall buoy bombs to ensure that even a near miss would be effective. Dive bombing. An aircraft diving vertically minimizes its horizontal velocity component. When the bomb is dropped, the force of gravity simply increases its speed along its nearly vertical trajectory. The bomb travels a virtually straight line between release and impact, eliminating the need for complex calculations. The aircraft simply aims at the target and releases its bombs. The primary source of error is the effect of wind on the bomb's flight path after release. As bombs are streamlined and heavy, wind has only a slight effect on them and a bomb is likely to fall within its lethal radius of the target. Bomb sighting becomes trivial, requiring only a straight line of sight to the target. This was simplified as the aircraft was pointed directly at the target, making sighting over the nose much easier. Differences in the path of different bombs due to differing ballistics can be corrected by selecting a standardized bombing altitude and then adjusting the dive angle slightly for each case. As the bomber dives, the aim could be continually adjusted. In contrast, when a horizontal bomber veers offline while approaching the bomb release point, turning to the angle that would correct this also changes the speed of the aircraft over the ground and thereby changes the range as well. In the 1930s and early 1940s, dive bombing was the best method for attacking high-value compact targets, like bridges and ships, with accuracy. The forces generated when the aircraft levels out at the bottom of the dive are considerable. The drawback of modifying and strengthening an aircraft for near-vertical dives was the loss of performance. Aside from the greater strength requirements during normal horizontal flight, aircraft are normally designed to return to fly straight and level. But when put into a dive, the changes in forces affecting the aircraft now cause the aircraft to track across the target unless the pilot applies considerable force to keep the nose down, with a corresponding decrease in accuracy. To compensate, many dive bombers were designed to be trimmed out, either through the use of special dive flaps or through changes in tailplane trim that must be readjusted when the dive is completed. The Volchave engines mostly used by the RAF and RAF in Burma was designed to be trimmed for diving, with no lift to distort the dive. The drawback was that it flew nose up in level flight, increasing drag. Failure to readjust trim made the aircraft difficult or impossible to pull out of a dive. A dive bomber was vulnerable to low-level ground fire as it dived towards its target, since it was often headed in a straight line directly towards the defenders. At higher levels, this was less of a problem, as larger AA shells were fused to explode at specific altitudes, which is impossible to determine while the plane is diving. In addition, most higher-altitude gunners and gunnery systems were designed to calculate the lateral movement of a target while diving. The target appears almost stationary. Also, many AA mounts lacked the ability to fire directly up, so dive bombers were almost never exposed to fire from directly ahead. Dive brakes were employed on many designs to create drag which slowed the aircraft in its dive and increased accuracy. Air brakes on modern aircraft function in a similar manner in bleeding off excessive speed.